This session will study what do you mean by the transient stability. Before moving into the stability, transient stability studies, then we'll see what are the small signal angle stability, then how we are comparing this signal dynamic angle stability with the transient stability. We know that the ability of the power system to maintain synchronism under small disturbances, that is come under small signal angle stability studies. If the distances are very small, in that case in the form of small variation in the load generation, then that is fall under the small signal angle stability studies. Then the system is regaining its synchronism, it is in the synchronism only. Then the disturbances are very small, and the equation, that is a system equation, are described, or a dynamics of the machines or the power system can be expressed in linearization of the system equation. There are two types of instability in that case. That is, one is steady increase in the angle. That is, angle delta is goes on increasing. It is because of lack of T, that is synchronous torque. That is, what do you mean by that? That is, there is a limit for the system to deliver the power. If the load is goes on increasing gradually beyond its limit, means it is a lack of T synchronous. In that case, the system is going to unstable condition. The another cause of instability is the rotor oscillations of increasing in amplitude, because of, if there is a disturbance occurs, a small disturbance occurs, then the damper windings have come into picture. But if the damper winding is not sufficient to counterbalance the rotor oscillations, in that case also there is a possibility of the instability in the system. The system response to small signal disturbances depend on the number of factors, that is the initial operating state, transmission system strength, type of the generator, excitation control. That is the response, that is in the case of event of changes, that is all depending upon the initial operating state. It is well less than the maximum capability of the system, then even though there is a small changes occurs, then the system is remains stable. Then at the same time the transmission system strength is also applicable. That is, if it is nearer to the system is operating nearer to the 80 or 90% of the transmission capacity, if the changes there occurring it is exceeding its 100% capacity, that also the system may go into the unstable condition. That is another factors what you have to see here is transmission system strength. And the last one what is specifying here, type of a generator excitation control. That is, if there is a proper the automatic generation control is there, then the system is regaining immediately its stable condition. This is all these points are, it is concerned to the small signals stability studies. That is, the disturbances are very small and the counter or can call restoring forces, they can act immediately. In that case, the system is regaining its stable condition. That is, it is subjected to very small disturbances. Then in contrast, the transient stability. That is, in the transient stability, it is concerned with the very large changes. In this case, there is no gradual change, there is a large change, sudden change. That is why he is telling that the first one, in practice, load changes may not be gradual. Further, there may be sudden disturbances due to several reasons. The one of the reasons for sudden changes in the system is sudden change of load. There is very large load coming to on the power system. That is a large change. The second one, there is a switching operation in the system. For some time, if there is overloaded, then what happens? Suddenly that particular line is switched off. Or some of the emergency purposes, you have to switch on some of the network. These are what we are calling is the switching operation. In that event also there is a large changes in the system condition. That is what we are calling as large change. Then the third category is the loss of generation. Some of the generator is going out of the order because of one or other reasons. That is also very large change in the system parameters. Then ultimately the fault is the cause of the large changes in the system. It may be generation, it may be a fault, it may be a switching operation, it may be sudden change in the load. In that case, there is a large change occurs. There is a large disturbance that occurs. Therefore, because of this, the large changes are due to sudden disturbances in the power system. The rotor angular differences, rotor speeds and power transfer undergo fast changes. That is because of the large system, definitely it affects there is a large change in the angle delta, that is a load angle delta, that is a rotor angle differences, there is a large change in the rotor speed. If there is a large load is increased, then suddenly there is a momentarily there is a speed is falling. Okay, there is a large changes means there is a large change in the rotor angle or rotor speed or the power transfer capacity. These are changing undergoing the large changes in their parameters, whose magnitude or depends upon the severity of the disturbances. If the disturbance is very large, then the consequences is also very large. That is large change in the angle delta, large change in the speed. That is there is a sudden drop in the speed. Then there is a change in the power transfer capacity. These are all the consequences of the large disturbances. For a large disturbances, change in the angular differences may be so large as to cause the machine to fall out of step. If the disturbances are very large, then angle delta go beyond its limit, it's a maximum capacity, and ultimately system is going to a synchronous position. This type of instability is known as transient stability. If there is a large changes or large disturbance in the power system, there is large rotor angle charges. In that case, it is not possible to regain once again the steady state condition. In that case, it is called as a transient instability. The transient stability is a fast phenomenon. It is there is sudden, there is occurs. It is no fraction of the seconds it occurs. Therefore, it is transient stability is a fast phenomena usually occurring within 1 second for a generator close to the cause of the disturbance. In that particular smaller period, you have to sense the severity of the fault, and you have to take the appropriate the counterbalancing measures to make the system stable, to operate the system in stable condition only. Therefore, the ability of the power system to maintain the synchronism when subjected to a severe transient disturbances were listed already. Different types of the transmission line short circuits, bus or transformer faults, or loss of generation, loss of large angle load. These are some of the cause of the large changes in the power system parameters. The resulting because of this large changes involves a large change in the rotor angles, power flows, bus voltage changes, and other system variables, and is influenced by the non-linear power angle relations. The angle, that is a relation between power angle relation, as a non-linear in this particular case. If the resulting angular separation between the machines, that is the number of machines they are operating in the parallel, if the fault is very severe, in that case the change in the angular separation between the machines remains within the certain bounds, then the system maintains synchronous. Otherwise, the system is going to the unstable condition. The loss of synchronism due to transient stability will usually be evident within 2 to 3 seconds of the initial disturbances. That is, within that only you have to take the corrective measures. The fault is usually assumed to be cleared by opening the appropriate breakers. Then the stability study period is usually limited to 3 to 5 seconds. That is the transient stability you have to study between 3 to 5 seconds. If going beyond that one, then there is no use because the system is losing its synchronism. Then with the help of this the graphs, how exactly under the change in the rotor angle, how we are classifying into the system is a stable, unstable under the small disturbances and the large disturbances I am demonstrating here. That is, if the load angle or a power angle, if it is changing in the event of a fault or in the event of any small changes, the angle is increasing and once again it is decreasing and it is oscillating and settled into new value, that the system is remains the stable. In the event of a large disturbances, if the angle delta is goes on increasing, in that case the system is losing its synchronism. Okay, that I am demonstrating here, that you can see here. That is, in the event of a small changes, initially it is operating at this particular point. Because of the small disturbances, angle delta is increased. And after attaining its maximum value, then what happens? It goes on decreasing and it is damping, that is slowly it is decreasing. Ultimately, it is settled down to new angle delta here. New angle delta here. Means now in this case the system is stable. That is, the angle increases to a maximum, then decreases and oscillation with a decreasing magnitude until reaches its steady state condition, then it is called as the system is stable. Because angle delta in the event of disturbances is changing definitely, but it is oscillating, but with the decreased oscillations and ultimately it is settled down to an event. Then this type of in this case the system is remains stable. And I will consider a second case here. In the event of a large disturbances, you can see here the angle delta is goes on increasing. In this case, the system is losing its synchronism. That is first swing instability. That is, the rotor angle steadily increases until loss of a synchronism caused by insufficient the TS or synchronizing torque. In this case, the system is goes into unstable condition because angle delta is goes on increasing with respect to time. And there is a third case here, you can see here. Initially there is change in angle delta, it is slowly increasing and ultimately it is not settled down to new value as in the case of case 1, but the angle delta is afterwards, after oscillation, it is goes on increasing and the system is goes into unstable condition. This is what we are calling is a stable on a first swing. That is, it is stable for a first swing here. It is increased and it is decreased, and it is until this it is stable. But here afterwards, the damping or the oscillations are goes on increasing. Ultimately, the system is goes into unstable condition. Okay. Therefore, I am giving the brief view of a historic view of these stability studies here. That is, the power system control recognized as an important problem in the 1920. That is, they are not bothered about the stability, what is the load, what is the demand, what is the generation, what is the balance between load and generation, all those. They are only the concentrating on in 1920s, that is the power system control recognized as an important problem. That is how to control the power. That is how to generate, how to control the power. And in 1970s and 1980s, then because of these changes, that is imbalance between the demand and the generation, in that case there is the change in the frequency, because we know that when the load increases the frequency will fall, or if the load is decreased suddenly then the frequency will rise up. In that case, in this 1970s and 1980, when there is a change in the frequency level, they are given the concentrate on frequency stability problems and related control solution. For that, they are finding the how to control the frequency to make it the frequency at the specified value, either 50 Hz or 60 Hz. Subsequently, in the 1980s, there are the several control designs. They are come up with the power system oscillation damping and voltage regulation. They are thought of then the change in the frequency is because of the change in the system, the parameters, and ultimately how to control that one, then how to minimize the oscillation, then what is the damping, how you have to counterbalance this damping, and how to you have to bring back the voltage to the specified value by the use of the voltage regulation. They are given the much concentrated on in 1980s. The subsequently in 1990s onwards, there is a supplementary controls will come into picture for very small changes, how there is a excitation can be changed so that there is a automatic generation control, then static power compensation, and there is a HVDC also come into picture in the 1990s, and also flexible AC transmission system, that is FAXOS also. They are given a much concentrate on this particular the period, that is 1990s. Then from 2000 there is a onwards, then they are concentrating on the phasor measurement units, that is in each and every point of the power system they have got a small PMUs, then they are collecting the data and sending to the energy management system, so that the system should be sensed very easily, that is gathering the data, and in the energy management system itself they are controlling what are the faults and how to clear the fault. The trust is all given on the PMOs and the automation part from the 2000 onwards. This is about a historical review of how the different studies takes place in the different period.